Good day, everyone. I am Irma Jane Pagaura. In this video, we will be tackling about the 4 cycling group tackling the 4 learning outcomes. 1. Explain the structure of a cyclic group and determine examples and non-examples. 2. Derive properties of cyclic based on exploration. 3. Prove the properties of cyclic groups. And 4th, apply relevant theorems to determine the subgroups of a given cyclic group and draw its subgroup lattice. So, now let us start. So groups are classified according to their size and structure. A group structure is revealed by a study of its subgroups and other properties, such that whether it is abelian, that might give an overview of it. So cyclic groups have the simplest structure of all groups. So here's the definition of the cyclic group. Group G is a cyclic if there exists A of any G such that cyclic subgroup generated by A equals all of G. That is, G is equal to NA parallel to N such in all Z, in which case A is called a generator of G. The reader should note that additive notation is used for G. So, let's look at a few examples of cyclic groups. A classic example is the group of integers under addition. The integers are generated by the number 1. To see this, remember the group generated by 1 must contain 1. The identity element 0, the additive inverse of 1, which is negative 1, and it must also contain all multiples of 1 and negative 1. This covers all the integers. The integers are a cyclic group. Now, let's proceed to the properties of cyclic group. I will be sharing one fact about cyclic group.
So, cyclic group satisfies the commutative property. Now, I'm not going to show the formal proof here, but I want to give you an idea of why that should be true. All elements in a cyclic group are powers of a single element called the generator. So that means that any G and H that I pick up out of the group are going to be A to some power. So maybe G is A to the N, H is A to the M. So the question is, what happens when I operate G, operate H, multiply them together? Well, all I'm doing there is I'm multiplying together a string of A's with another string of the same A. So if I have N of them first and then I have another set of M of them afterwards, then how many do I have in total? So I have N plus M. Remember how I said in the introductory video that we see shades of the additive group of integers everywhere we look when we're dealing with cyclic groups. And this is an example. When I multiply 2 elements of a cyclic group together, what happens to their exponents? Their exponents just end up adding together. So this is another reflection of this idea that the integers that are in the exponents are really what's driving the structure in a cyclic group. When the group is infinite, it's the additive group, the infinite additive group of integers. And when the group is finite, then arithmetic that happens to those exponents ends up being arithmetic of additive equivalence classes, modulo n. But that's all that there is to it. Exponents are completely driving the car in a cyclic group. So that's the first fact. Is that anytime we're dealing with cyclic groups, we know that we can take the commutative property for granted. Every cyclic group is abelian. The congress is not necessarily true, as you should convince yourself. There exist examples of Boolean groups that are not cyclic. Now, let's prove the properties of cyclic groups. Facts say that if G is a cyclic group, then the order of any element in that group has to be a divisor of the order of the group. Another way to say that is that the order of the group G is a multiple of the order of any of its elements. The elements inside of a cyclic group of finite cyclic group can have And because this is so significant, let's endeavor to write a proof of this fact again. First, assuming that the order of my group is finite, otherwise there's not a whole lot to say here because one of the divisor of infinity, so if G is a finite group of order n, then let me pick up an element of them, the group G. And I want to show that the order of G has to divide n. Why is that true? Well, my definition of a cyclic group, we know that this element G must be some power of the generator A, so there exists an integer such that G is a raised to that integer power. Let's call the integer K. So G is equal to the K. Now, how do we know first? First of all, that the order of G has to be finite. We can make the same argument that we made right here. The order of G has to be finite because otherwise all of its power is being distinct would imply that this group were infinite, so G has to have finite order. So let's call the order of G M. So now we're down to proving that M divides N is what we really need to show now. And if the order of G is M, that means G to the nth power gives me the identity element. But now we know two things about G. We know that its M power is the identity, and we know that G is the K power of the generator A. So let's smoosh those two things that we know together. We know that generator A has the order equal to the order of the group. Alright, so the order of A is n. That's what we argued for up here was our fact number 2, and so therefore this identity element is equal to the nth power of A, but on the other hand, G is equal itself to the K power of A. And so the nth power of G is the nth power of the K power of A. And by properties of exponents, again, here's the arithmetic of integers rearing its ugly head right when I write K powers of A. And in consecutive times, then in total, I have K plus K plus K plus K, M times power of A. So I have A to the K times M. But now, if I read this expression from the left side, of the right side, the exponents on my A's are the same. The K times M with exponent of A is equal to the nth power of A, and therefore K times M has to be equal to N. And since K, M, and N are all integers, this shows that M is a divisor of N, and the K is a divisor of N. Actually, it was M. It was that issues here. Sorry, that's a typo, but that is exactly what we're trying to prove. Alright, the order of G has to be a divisor of the order of the group, and that completes the proof. So far, we've gotten quite a bit. Every cyclic group is a billion. The order of its generator is the same as the order of the group, and the order of any elements has to be a divisor of the order of the group. These things are all cyclic groups. Moving to the last part, let's have the theorem or the definition of the group and the generator. So a group G is cyclic. There exists an element A in the group such that G equals the group generated by that element A. In fact, we can also say what a generator is. A generator of a group G is an element A and G such that G equals all those powers of A for A to the N, where N is an integer and this is a multiplicative notation. If I wanted to rewrite this using additive notation, I could say instead that I have A equaling instead of A to the N. I would have N times A for any integers N. So this is additive notation. And so we see that Z6 is cyclic with generation 1 and 5, while S3 is not cyclic. Okay, so here's the definition of a cyclic group, and here's the definition of a generator. And we saw that Z6 is cyclic since 1 and 5 generated Z6, but what about Z sub 7? C sub 7 is is the set consisting of the integer 0, 1, 2, 3, 4, 5, and 6. And the binary operation this time is addition modulo 7. Here's the group table for Z sub 7. And let's look at some cyclic subgroups. So we know that mod 0 is probably not going to be that exciting. How about 1? So if we look at the group generated by 1, we see that we would have 1, and then 1 plus 1 is 2, and 2 plus 1 is 3, and so on. And we would end up getting the entire group here. So thus seem to work here. But what about 4? So put for work days, so we could try for 4, and then 4 plus 4 is 8 mood 7 is 11 is 1 11 plus 4 is 5, is 5. That's okay. 5 plus 4 is 9, but 9 with 7 is 2. 2 plus 4 is 6, okay, and then 6 plus 4 is 10, mood 7 is 3, and 3 plus 4, 7, and 7, mood 7 is 0, so that worked too. And I leave it to you to check, but if you try any of other numbers other than 0 here and try and give the generated cyclic subgroup from that element, you'll see that it does indeed generate the entire group. And in fact, for any integer n greater than 1, we see that Z sub n is generated by 1, and also n minus 1. So this right here, that it's generated by 1, that kind of makes sense, because you do 1 plus 1 each time, and you generate the entire of figuring out which element of Z sub n will actually generate the entire group.
So, that's all for my report. Thank you for watching.